Hello, everyone. For this presentation, we're going to talk about cement composition and hydration. So during this project so far, you have gone outside on a field trip. You have looked into concrete and what the components are and what's kind of the difference between cement and concrete. And we've kind of discussed that a little bit. We're going to go into more depth about what is actually in concrete and then how the process of hydration helps harden the cement. And so one of the questions we asked in the very beginning of the unit was what was the difference between cement and concrete? And your answer is that concrete has cement in it, except it has aggregates in it. And we're going to learn what those aggregates are today. So if you look at the composition of concrete here, this is percent by volume, you'll see that you have that cement in it. But the cement itself actually makes up only about 9 to 15% of the total concrete. You have another 15 to 16%, which is water. So this creates the paste, which would harden essentially and make your concrete. And then the difference between our cement, which you've made, which would be these top two, and the concrete is that we add these aggregates. And these aggregates are fine aggregates and coarse aggregates. The fine aggregates are going to be the smaller ones. The coarse ones are going to be the larger aggregates. And if you look here, this makes about 70% of our total concrete. So the actual cement that you're adding is only 9 to 15% of your total concrete. Here, this is a different visual. You will see here that your water is the blue and your cement is this gray portion. And then the coarse aggregates are going to be the 40% in the green, and the fine ones is going to be the 36% in the red. And then if you look at this picture, you will see that these bigger rocks here, those are going to be our coarse aggregates, and then the tinier ones that you see around are going to be our fine ones. And we did have many people go outside, and when we asked what were some components of concrete, a lot of you did say that there was rocks and sand, and you guys would be absolutely correct. So if you look at this picture, you can see those aggregates that are inside it. The cement that you made inside was just cement and water, so you wouldn't have these aggregates that were added there. So what exactly is an aggregate? It is a material that is added to cement to increase the durability and the strength of the concrete. Here you can see that I divided them between your fine and your coarse aggregates. These are just some examples that could be fine aggregates. You have some fine gravel, sand, and crushed stones, and these are going to be less than 3/8 of an inch. And then you have your coarse aggregates. Those are going to be your bigger rock, stones, gravel, and cobbles. Those are going to be somewhere between 3/8 and 1.5 inches. And so those can be a lot bigger in terms of the aggregates. Okay, so why actually are we adding them? What's the point of adding them in to help the concrete become stronger? So it helps make it more compact. So if we look at these pictures over here, these would be if everything was the same size. And down here, you can see all the gray area is like the plain cement or paste that's left over. And as you keep adding more and more, both larger and smaller ones, you can see that they become more compact, meaning that these circles are able to fill in all these little tiny little gaps. They can become closer together. And if you see here, the leftover paste or like just the plain cement is almost nothing compared to what we started with over here. So this allows it to become more compact and contributes to the overall strength of the concrete. Another thing that we noticed while we were outside is that there were some metal in the sidewalk as you were walking by. And so that metal that is added is called rebar. So rebar is known as a steel reinforcing rod in concrete. I have some examples for you on the other side, but it helps reduce cracking and breaking when tension is added to concrete. So if we look at this picture that's over here on the left-hand side, you have this chuck that is on a concrete beam, and there is no reinforcement here. So when all the weight on the chuck is here, there's really nothing to help support it. So you can see that the base starts to crack. And that's because you have tension here. That's the weight of the chuck is forcing it down. And it's just not reinforced enough for it to be able to hold the whole weight. So if you look here in the third picture down, you will see that there's a rod that is added. And it holds the concrete together pretty well, and it stops the beam from cracking. But if we stretch the rod over, so this last picture, it is over each edge, it makes it very, very strong. So this last picture is what we normally see in like our bridges and our roads. We really want that reinforcement so that your roads don't crack, or especially your bridge as you're driving across it. You don't want it to crack and start breaking. So you will see like here, these are examples of your rebar. This is like in what you saw in the sidewalk around the building. It wasn't this fancy, but there was still some there. These are also some examples of some steel bars through the cement. And again, it's just there for the reinforcement to help prevent any cracks when weight or tension is added onto that concrete. Okay, so what actually happens when water is added and how does it actually harden? So this process is called the hydration of our cement silicates. So when water is added to your cement, the calcium in the cement starts to go into the solution. So these little gray blobs here, these are going to be your cement. It's dry. The water hasn't kind of been into it yet. And as you can see over time, what happens is the pH level will rise and the silica portion of the cement will start to dissolve. So that's what these little like black and pink little dots are. And if the pH level is rising, things are starting to dissolve within that water. And as that happens, your calcium silica hydrate starts to harden. And that is this lighter color around our original cement that we had. And when that starts to form, it will get bigger and bigger and bigger and start to clump together. So as we can see over here, that calcium silica hydrate, which is known as the CHS over here, it starts to get bigger and starts to impinge on each other or get closer. And finally over here, you can see that they're touching. So over time, this gets larger and starts to harden. And when it gets big enough and it's touching each other, it happens about after 4 to 8 hours after the water is added. They start to grow together, and we call that as cement has set. But as you look over here, you should have seen on the graph that we gave you last week, it really does take about 28 days for the cement to fully harden. And that's because if you look at this graph here, your hydration keeps adding and adding and adding, and it starts to level off at about that 28-day mark. Same thing with the capillary porosity. As it's going down, it starts to level off at about 28 days. So even though we say that it's set after 48 hours, the total process of it curing or hardening does take about 28 days. And then here's just a different picture of it. You can see in our other picture, it was this like gray, that's our silica hydrate. In this picture, you have these little spiky things. So those are reaching out, and that's going to help harden the cement. This is a zoomed in version of it. And that's all I have for you.